Hi everyone, my name is Pierre Ayoub, I work at Eurocom, and today I will present to you our paper entitled Reproducing the Spectre Attack with Gem5, How to Do It Right. This is a joint work with Clementine Morris, and thanks for being here. I will introduce the talk and the work by a bit of context. So who am I? Last year I was an intern student at Eureka in France, and currently I work at Eurocom as a PhD student. So this work was done at the Eureka last year. About this presentation, the initial idea was to know if transient execution attacks could be simulated. So we used the spectre attack to study this kind of attack, and the reasons that the simulation of this kind of attack is interesting, it's because they rely on tiny CPU details to work, because this kind of attack exploits the microarchitecture of the CPU to work. So by nature they are difficult to simulate. Moreover, they are hard to study and reproduce for a researcher, so the simulation could be very helpful. So we wanted to compare a real system and a simulated system. As a real system, we used a Raspberry Pi with an ARM Cortex-A72 processor, and for the simulator we used gem5, which is a microarchitectural simulator. That means that in software it simulates all the hardware components of the system. So the goal was to have an attack that works similarly on both systems in order to compare the faithfulness of the simulation. And finally, we wanted to know how gem5 could be useful for a security researcher in his works. Unfortunately, the theory is rarely the same as the practice. So there were some problems, and the first one is that the available Spectre implementations failed on our Raspberry Pi. It leads to the development of some guidelines and custom guidelines about how to develop and reproduce this kind of attack, and a custom implementation on our side. Secondly, reproducing a microarchitecture in gem5 is impossible. There is too much details and too complex, so we have to focus on specific element of the microarchitecture. Finally, gem5 needed some extension to compare it to the real system, so we had to patch gem5 to be able to do some measurements to compare both systems. So in summary, our contributions in this presentation and in our paper are the guidelines that we think are important for microarchitectural security research. We demonstrate the usage of gem5 to both helping attack development, reproducing, and understanding. We also demonstrate the simulation of Spectre and the evaluation of the faithfulness of the simulation, and finally the different requirements of gem5 to simulate those attacks. So this is the plan of today, the related work, a bit of background, talking about our implementation, and finally the faithfulness of the simulation. So, about the related work, as far as we know, there is no specific literature about the simulation of microarchitectural attack in general, so there was no paper at all to base our work on. We found only one blog post of Jason Low Power, which is a gem5 developer, which was able to visualize the Spectre attack on gem5, on a gem5 system. It was on the x86 architecture, and it was with the default gem5 configuration, and at the left you can see a pipeline visualization of the simulated processor, and we will detail this later in the talk. So after seeing this blog post, we wanted to go deeper and to understand more on how it works and how it can be useful, and what we can do with that. So let's dig into the Spectre attack itself. To understand what is the Spectre attack and how it works, we have to understand what is a transient instruction. For that, we have to see the CPU as two separated domains, the architectural one and the microarchitectural one. The architectural domain is what does the programmer see, the registers and the instruction stream, and our microarchitectural domain corresponds to the computing resources that performs the computation. Sometimes, for some reason, an instruction could be executed while it should not have been executed. It's just here. In this case, the processor performs a revert to the previous microarchitectural state. But for the programmer at the architectural domain, it's like no unauthorized instruction has been executed. But in reality, the revert is not perfect. So when intrusive execution happened, where it affects the CPU microarchitectural state, leaving the architectural state as prior as the execution, it can reveal a secret if the microarchitectural states change depend on a secret here. So the spectre attack that we used targets the branch predictor. This is a CPU unit which is used to predict the instruction flow when branches are encountered, and the prediction is dynamic. That means that it is based on previous execution, and by manipulating previous execution we can manipulate the prediction. So the branch predictor use a structure which is called the PHT. It's a table of some contours, and it is indexed by a history pattern, itself determined by the previous outcomes of the last branches. So the goal of the spectre attack is to increase those contours, because when a contour is at its maximum, the prediction will be at the taken. The branch will be predicted as taken by the branch predictor. So how does spectre work internally? We need a target. This is a victim function with the x controlled by the attacker, and what is important here is that we have a bound check here. This is the attacked branch, and here we have two load. The first load here will be the secret if x is controlled by the attacker, and the attacker has access to array2 to probe the microarchitectural domain later. Here we have the four possibilities, and the spectre attack happened when we follow the red path here, when in reality the branch is not taken, but in reality but the prediction is that the branch is taken. So yeah, if x is malicious, then this will be the secret value that we want to recover. So the steps of the attack, there is 3 steps. The first one is the training phase, where we execute a lot of time the branch with a valid index to increase the PHT contours. Then there is the attack phase, where we send the malicious X computed with the secret address. Finally, there is the recovering phase, where we probe the microarchitectural domain to recover the loaded secret, which is loaded transiently. So we have to find the element of the array2 that has been cached with the flash and reload attack. Basically, we load every element of the array, we measure the time taken, and when we find a quick load, that means that this element has been cached. Then we compute the secret based on the value of the address of the element that has been cached. So because the attack was complex to reproduce with already existing implementation and complex to develop on a vulnerable processor, we wrote some guidelines to help with this. There is way more details in the paper. To develop the attack, an attacker has to take care about the compiler, version, optimization. Also, there is a lot of different methods to measure the time taken for the covered channel. This is an important point. There is also the prefetcher and reordering mechanism. The prefetcher loads ahead of time some memory elements into the cache, and reordering is a mechanism of the processor to reorder the instruction stream. So in general, when we deal with this, we make some blind assumptions because it's internal mechanisms of the processor. And we will see in the next section that gem5 can help to resolve this kind of problems. And moreover, there is the transient execution window, which is basically the time during which transient executions can happen. For example, we have 2 conditions here, and we see that the condition at the right will be way more longer than the condition at the left, because we have a flood conversion and a division. So this can very help a lot when developing this kind of attack. There is also a lot of comments and of tips into our implementation, so our code is available. Feel free to look at it. Finally, there is some parameters to take care when we reproduce some kind of this kind of attack. We have to pin on a core the attack. We have to check the page size to fix the frequency of the core of the CPU, and finally to check if there is some mitigations that are enabled or not on our system. The gem5 simulator is a microarchitectural simulator, so-called cycle accurate. That means that it simulates every cycle in each hardware components of the system. It is a state-of-the-art project started in 2011. It is composed of two parts: the C++ part, where all the logic of the different components is programmed, and the Python interface that the user use to build systems and tie up components together. So gem5 supports a lot of architecture, and we are especially interested into the ARM architecture, which is well more supported than the x86 architecture. And gem5 has some generic microarchitecture, so especially here for the CPU models, so there is some very simple in-order CPUs to 7-stage out-of-order pipeline processors, so way more complex and way more faithful. But we have to understand that there is no specific model for one specific microarchitecture, or at least it's very rare. So we have to focus on specific elements in the microarchitecture that we want to reproduce and plug them into more generic models of microarchitecture. There is also a lot of different branch predictions algorithms implemented into gem5, and we will talk of them later. So how to use gem5? This is just some snippets of code on how to, for example, configuring parameters using Python associations, how to instantiate some components using all the Python logic in terms of conditions, how we can connect components together by using the port mechanisms, which again work just by using Python assignations, and finally a demonstration of on how we can use some the different Python structures to build more complex variables and do complex things. So to launch a simulation, it's very simple. It's done in Bash. So we have the system here, system model, which is a Python file, and we can give some arguments. Then we will have to connect to the simulation terminal, and we will see the kernel booting up. And after several minutes, we will open a shell on the simulated system, and we will show this. Which is the simulated system, and we have a shell on the simulated system to do whatever we want in the simulation. So let's talk about the main techniques that we want to present here, which is the benefits of pipeline visualization. Gem5 has the control of any element in the system, so it can output the state of all the element that we want and that we request. And there is also Conata, which is a pipeline viewer that allows to graphically visualize the pipeline of a simulated processor. So this is some examples, and we will present you some visualizations of the spectre attack of the different scenarios. Here, this is a successful attack. So we have first the branch condition here in the red square, which is way longer than the rest of the instruction. Here we have the victim branch at the left, which is longer than the following instructions here, and this branch is longer because the condition takes is long to compute because of the flushed memory element and the division, which is long. So here we have some flushed instructions which are gray shaded, and these ones are not executed at all at the bottom, but at the middle and at the top of the gray shaded square, instructions are executed transiently, because we can see that they are fetched, then decoded, renamed, dispatched, and issued. Each color corresponds to a pipeline stage, and at the left we have the instruction stream, and from left to right this is the cycles, each cycles. So here in the transiently executed instructions, we have the transient load here that leaks the secret, and that will modify the cache state transiently. So this is a successful attack scenario. We can observe different scenario. Here this is the branch predictor that is being trained by the spectre attack, the first phase. This is exactly the same instructions as before, but the only difference is that here the instructions are not transiently executed comparing to the previous slide. So they are not gray shaded, and they are committed at the end of each instruction stage. And finally, here we can see a spectre attack that is defeated by the branch predictor. How do we know that? It's because here, so here at the top we have the branch condition, the victim branch as before. Then here we have some instructions, and here at the BL mnemonic here we jump into the flush and reload part, and we should jump here only if the attack has been performed, so with the malicious index. And here we saw that there is no transiently executed instruction, so that means that the branch predictor was not well trained by Spectre to have a mispredictions that will lead to a transient execution. So this scenario is very interesting because it allows us to know why the Spectre attack doesn't work this time, as while previously, before using a simulator, we were completely lost. That means that we could make blind assumptions, but we can't really see what is going on inside the processor. And here we visualize the pipeline, but there is no, at my knowledge, other visualizations yet, so graphical visualizations, but gem5 is able to output the state of any components in the system. So we can, for example, have information of what is going on inside the caches, or what is going on inside the branch predictor, each structures of the branch predictor. So it could be very powerful to understand what is going on in microarchitectural attack, what is going on inside the CPU, to understand why it works or why it doesn't work on this system, or with this architecture, with this countermeasure, and so on. And maybe in the future it would be very great to have more visualization features. So let's look at our implementation. First, the implementation of the Spectre attack itself on the Raspberry Pi system. The already existing implementation failed to perform the attack correctly for several reasons. So we had to develop custom implementations with the following requirements. The first one was to have stable results to be able to compare the both systems reliably. We wanted also an implementation that follows our guidelines, and an implementation that is usable in the same way both on the Raspberry Pi and on gem5. Finally, our implementations should output some metrics to be able to perform some measurements. So the steps of our implementation were the following. We took the port kosher implementation for x86 and we ported to ARM. Then we applied our guidelines for mainly on the prefetcher, on the reordering, and the transient window part. Then we had a working implementation, and with some optimizations we get the stable results. Then we had to implement the metrics measurement, and we were ready to compare the attack between the real system and the simulated system. For implementing the gem5 system, there was also several steps. First, we start by a syscall emulation system. That means that gem5 runs emulates all the system calls and don't simulate any operating system. Then we had some caches for the fresh and reload part, and we added the branch predictor. And then at that time we had the Spectre that work on our system. We switched to a full system simulation to have gem5 simulating the entire Linux kernel and an operating system to have a more faithful simulation. And finally, we patched gem5 to get perf event working, and at that time we had the Spectre that works and the measurement that works. So the goal was to get enclosure of the ARM Cortex-A72 of the Raspberry Pi, but only on specific elements, so mainly for the caches and for the branch predictor, because we can't reproduce all the Cortex-A72 into gem5. There is too much hidden details, and there is too much work also. So this is how our gem5 system looks. Here we have our CPU at the bottom. We have the four cores here, the L1 caches, the L2 caches here, some components to tie up all the components together, and the platform, the real view platform of the ARM system, which handles all the memory mapping and interruption handling. This is the configuration of our branch predictor. The scheme might be impressive, but it's not. In fact, at the left, this is what we already seen, and this is how the branch predictor of our ARM Cortex-A72 works. And at the right, this is the branch predictor that we used on gem5, the BMod predictor. In fact, the BMod predictor uses two PhD, one for the mostly taken branches and one PhD for the mostly not taken branches. But when considering the spectre attack, since the spectre attack trains the branch predictor to take the victim branch as a mostly taken branch, for that particular branch, the BMod predictor should only consider the left PhD, that means this one. And if we don't care about the PhD at the right, it's equivalent, both designs are equivalent. So this is in theory, and it will be verified in the next section. So a simulation which is working but which is not faithful will not be so useful for a researcher, because if something works on the simulation but not works in reality, or the opposite, it will be a waste of time. So we measure some metrics. For example, the first one is the number of retrieved bytes by the attack. This is an architectural metric, and the attack works similarly on both the real system, the Raspberry Pi, and on the gem5 system. This is the attack works the same in terms of success. We measure also the number of iterations, which can represent the difficulty of the spectre attack to retrieve the given number of bytes, and it was 2 times easier on the gem5 system. Same for the number of cycles, which represent the time taken for the attack. It was 3 times faster on the gem5 system. So all of this means that the gem5 systems has less noise than the real systems, but it's the same order of numbers. For the cache misses, we had an aberrant result, because surely because our code had a problem on this matrix, so we can't say anything about that currently. And for the mispredicted branches, which is maybe the most interesting result, the number of mispredicted branches are very, very similar on the gem5 system and on the real system. So that means that the attacks at this point, for the considering the branch predictor, works very similar between the two systems, which is very encouraging for using this kind of simulation to do research, development, or reproduction into with this kind of simulator. So let's conclude about our work. If simulation becomes widely used, it would be very easier to reproduce older attacks, to better understand and experiment with them. And with faithful models, which is a very complicated challenge, of course, researchers could use the simulator itself to discover new vulnerabilities, which is maybe the most interesting goals of this kind of work. But there is some drawbacks, of course, and one of the main drawbacks is that the simulation is currently pretty slow. To run a spectre attack, you may count 1 to 5 hours. And finally, the simulator gem5 still needs some improvements and some extensions to implement new technologies, for example, and to implement new visualizations that can be useful. So in summary, we saw that it's possible to simulate microarchitectural attacks. This is the first step, and also to being accurate in the simulation. And we also saw how visualization could be a very powerful technique to understand the microarchitecture behavior of the attack and to see what is really going on into the CPU during an attack. So we have a website with the URL just here that demonstrate and guide you in all our work if you want to reproduce or to extend it or just to see a bit more on the visualizations or the code. So this is the end of the presentation. If you have any question, I will be happy to answer. And you can also reach me at pierre.ayub@euricom.fr. And if you have any question and I can help, I will be happy to do so. Thanks for your attention.